In about 5 billion years, our sun is going to die. It'll swell into a red giant more than 100 times its current size. It's definitely going to swallow Mercury and Venus, and it may even swallow Earth, although the last part is still being debated. After eating potentially 3 of our solar system's rocky planets, the sun will blow off its outer layers and shrink down into a white, hot ember about the size of our planet. This stellar remnant is known as a white dwarf. So that's the end of the story for most of the inner solar system. But what about the outer planets? Jupiter, Saturn, Uranus, Neptune, do they survive? Honestly, we've never really known. But a brand new discovery just gave us our first real glimpse of the gas giant's possible fates. Because 80 light years away, the James Webb Space Telescope just studied a Jupiter-sized planet that lived through exactly this, the death of its star, and it came out on the other side. How it survived is genuinely one of the strangest things I've read all year. This is WD 1856b, and it might be a preview of our own solar system's final chapter. Let's get into it. Okay, first, I want to cover some numbers because honestly, the numbers here are ridiculous. WD 1856b was first spotted back in 2020 by NASA's TESS telescope and the old Spitzer Space Telescope. It orbits a white dwarf called WD 1856, about 80 light years away from us here on Earth. And here's the first weird part. The star is now roughly the size of Earth because it's a dead stellar core, as I mentioned earlier, while the planet is about the size of Jupiter. So this is a planet that's around 7 times larger than the star it orbits. The planet literally dwarfs its own star. It's also worth noting that this white dwarf isn't alone. It's accompanied by 2 other stars, a pair of red dwarfs, in what's known as a triple star system. Keep that in your back pocket, it's gonna matter later. Now, here's the second weird part. The planet whips around that dead star once every 34 hours. 34 hours. Think about what that means. The planet's entire year is shorter than your weekend, and it's sitting about 50 times closer to its star than Earth is to the sun. And that's a problem, because if we rewind billions of years, before the star had died, it went through its red giant phase. It puffed up enormously. Any planet sitting that close would have been inside the star itself. It should have been vaporized, destroyed, gone. And yet, there it is, still orbiting, not destroyed, not gone. So, the obvious question is the one the whole team wanted to answer. How on earth did this thing survive? Well, this is where Webb comes in. The team, led by Ryan McDonald at the University of St. Andrews, used JWST to watch the planet pass in front of its star, what we call a transit. And that transit gave them 2 crucial clues. Clue number 1, the planet's mass. The transit pinned it down to somewhere between 4 and 11 times the mass of Jupiter, so a serious heavyweight, firmly a gas giant. Now, obviously earlier I said WD 1856b was about the same size as Jupiter, and that's true, but it's just far denser. Several Jupiters worth of mass packed into a Jupiter-sized package. Clue number 2, and this is the big one, its temperature. When the planet crossed the star, infrared light dropped less than other wavelengths. That leftover infrared was heat coming from the planet itself. And when they measured it, the planet came out at around 126 degrees Celsius, or about 260 degrees Fahrenheit. Way hotter than it has any right to be, if the only thing warming it was that tiny, faint dead star. So now there's a second mystery stacked on the first. Not only did the planet survive, it's weirdly warm. Where's the heat coming from? Here's the clever bit. There's no energy source that could be heating the planet today. So the team, with Christopher O'Connor at Northwestern doing the detective work, realized that the heat has to be left over. Residual warmth from something that happened in the planet's past. And if you know how fast a gas giant cools down, you can run the clock backwards and work out when it got heated. And the answer points to a specific story. The heating happened somewhere between 3 and 5.5 billion years after the star had already become a white dwarf, which rules out the scary version. The idea that the planet was swallowed during the red giant phase and somehow clung on. Instead, it tells us this. When the star was dying, this planet was far, far away, on a nice, safe, wide orbit, well out of the reach of the bloated red giant. Probably similar to where our own solar system's gas giants sit today. It rode out the whole thing from a distance. Now, remember those 2 red dwarfs I told you to keep in your back pocket? This is where they come in. The leading explanation is that over billions of years, gravitational nudges from those companion stars slowly reshaped the planet's orbit, stretching it into an extreme ellipse that sent it screaming past the white dwarf on every lap. And each close pass, the dead star's gravity kneaded and flexed the planet like a stress ball, heating it from the inside while gradually shrinking and rounding its path into the tight 34-hour loop we see today. It hit its maximum temperature during that inward death spiral, and it's been slowly cooling off ever since. Oh, and one more thing. Webb also caught the planet's atmosphere. As starlight filtered through it, they saw signs of clouds and hydrocarbons, most likely methane. That's a genuine first. It's the first atmosphere ever detected on a planet orbiting a dead star. The team's already grabbed 4 more transits, so there's more data coming, and if anything interesting falls out of that data, I'll make sure to make a future video to cover it. So, why does a warm gas giant 80 light years away actually matter? Because we're looking at our own future. Hopefully, throughout this story, you've seen the parallels. Our sun will eventually follow the same path as this white dwarf. In about 5 billion years, it'll swell into a red giant, then shed its outer layers and collapse into a white dwarf. Jupiter and the other gas giants should be far enough out to escape being consumed, but their fates in the far distant future, still unknown. This new research lifts the veil ever so slightly on that future. When telescopes look out into outer space, we're almost always looking back in time. That's the nature of light. But this is the opposite. This is one of the first times we've been able to look forward, to see what could happen to the outer planets of a sun-like system after the star dies. As Ryan McDonald put it, it's like using a time machine to peer into the distant future of our own solar system. WD 1856b is a real, physical example of how a gas giant can not just survive its star's death, but end up on a wild new orbit around the corpse of its star. It's a little haunting, honestly. A giant planet circling a dead sun every 34 hours for the rest of time. That might be Jupiter someday. Well, that's it for today's story. The paper's out in Nature if you want to dig into the details. I'll link it below. If you enjoyed this one, please subscribe. I cover new space discoveries like this every week. And let me know in the comments, do you think Jupiter makes it? Does it survive the sun, or does it drift off into the dark alone? Thanks for watching, and I'll see you in the next one.